Thank you very much for having me here. I wish I could have come to a long program. I'm really sorry I couldn't join, but it's really great to be here at least for the workshop. Okay, so let's start. That is the kind of system we would like to simulate. Typical textbook image, you have all seen that. So I thought I'd jump right in. In an ideal world, we would be able to make a simulation for the whole system. But the system is really far too big, of course. And also, it's not really necessary that we simulate the whole system from first principles, because all the interesting bond-breaking, bond-making, the electronic dynamics, they go on here right at the interface. And so it's, I guess, all our common approach that we want to focus on a DFT-sized simulation cell. We want to simulate from first principles only the interfacial region. But, and that's the big problem, we have to ensure that whatever we have enclosed here in this interfacial region behaves exactly the same as if we were simulating the whole big system. So the bounded finite system that we have inside our supercell must really replicate exactly the behavior of the same region in the unbounded physical system. Okay, so the way we usually try to do this is via boundary conditions. Jörg has already talked quite a bit about boundary conditions. What we mean by boundary conditions is usually this boundary here. The one on this side is okay. Here and here we have periodic boundary conditions, but here we have a problem because we need to truncate the electric double layer. The way we typically do this is by introducing a surrogate model that goes here after we truncate the double layer. The surrogate model contains the charge that we have now cut off. Usually we'd have this long exponential decaying tail. So there is some charge here left in the double layer, and this charge is going here into the surrogate model. Then we can have a potential distribution like this. There will be a step discontinuity. We can use this to measure what is the potential difference between this point and this point. There is a way how we can relate this step, the size of the step discontinuity to the electrode potential. The counter charge that we have here is exactly equal and opposite in sign to the electrode charge we have over here.
Excuse me, why you call it electrical double layer? Because I know I call the electrical double layer those at a solid liquid interface. It's a little bit confusing to call it for me at least.
Oh, you mean this part here?
Yes.
Yeah, I like to call this a surrogate model because this replaces all the double layer that goes, all the rest of the double layer that we no longer have inside the cell.
That's not a double layer. It's the solvent. It's the solution. Why you call it?
Well, the double layer, the diffuse part, is fairly large. So if you cut this off to these typical concentrations of 0.1 mole, then you will still have some charge over here.
I thought that the double layer was something in a region pretty close to the interface in the usual.
Yeah, we tend to divide that into different parts. So the first direct adsorbed layer would be the inner Helmholtz layer. Then we have some solvated ions. That would be the outer Helmholtz layer. And then after that, we have the diffused layer, where we still have an excess of one particular ion species.
So, and at what level of theory and simulation are you treating this surrogate model layer?
I come to that. That's the part. That's the point of the talk, how you do that. So it's just about the setup for the moment. I actually wanted to say that a large class of the models that we have, a large class of the approaches is of this type, of this particular setup. How exactly you realize the surrogate model, or what we call the surrogate model, of course, other people call it differently. But no matter how we call it, there are different ways how this can be realized. So one way how it can be realized, for example, is by putting a charged implicit solvent here, like Environ, what you have been using. But there are other ways. So the point I wanted to make here actually is this is a common setup. Many people use it. However, most people so far have focused on replicating the mean of the potential, what I show here. Yeah? The black curve is the mean of the electrostatic, of the electrode potential. But the point I want to make is reproducing the mean potential is not enough. It's okay if you are just interested in equilibrium properties, like, for example, dielectric profiles, like we looked at the dielectric constant of nano-confined water. In that case, it's okay. Yeah? You can live with the mean of the potential. But if you look at reactions, then you may want to take into account that this is not a structureless continuum, but it's really a highly dynamic, a liquid environment. So for an ion desorption reaction, for example, as we have here, this ion needs to, first of all, it's a neutral atom. It has to charge, the electron has to go to the surface, and the ion has to go through this layer. And this is all highly dynamic. So the goal is we want to ensure that the dynamics we have here in this small supercell replicates the dynamics we would have if we had the huge system in a simulation. Richard was asking on this slide for the full cell that we have been using here. So I put the picture here. The idea is now the following. We need some kind of reference. As reference, we use this relatively large cell. Yeah? It's not terribly large. It's 25 by 25 times 80 angstrom. But we can use it approximatively as the thermodynamic limit. Now in this cell, we select a small subcell. The small subcell, that has the size of a typical DFT-sized region, yeah, like 10 by 10 angstrom. This cell, this boundary here, is fairly far away from the other side. So I assume, yeah, whatever kinds of boundary conditions we use here on that side, they should not impact too much what is happening here. In the thermodynamic limit, all the boundary conditions are the same.
Yeah?
Sorry?
It's done classic.
This is just an example. Okay. This is done classically, of course.
Yeah, okay.
Because that doesn't matter. Yeah? For the boundary condition, it doesn't matter whether you look at that classically or ab initio. Yeah? This is for illustrating the problem.
Yeah, it's fine. I just wanted to understand. I mean, there are differences, I think, but it's not. It's fine.
Okay, so for the huge cell, we compute the 3D electrostatic potential. And now from this 3D electrostatic potential, we cut out also only this small part here. Then we compute a planar average. And then as the mean, you get this particular potential. And you see at the interface, you have some oscillations, stratified water, and then you have a field here inside of the water.
Quick question. Are what are the boundary conditions you're using on the top and bottom in the supercell?
You mean here and here?
No, in your reference.
In the reference. These are periodic boundary conditions.
And when you grab them on the small cell, are they not going to be periodic?
No, they are not periodic.
Transverse direction? They're not?
No.
Okay.
So that's the point. Yeah. So here we just cut out a small region, and we require that in the end, however we set up the final simulation for the small cell, it must resemble exactly the same behavior as this cutout from the big cell. Because then we have the right physics. Yeah? If our small simulation cell replicates the behavior of the same region here.
Another question. So there you have a potential, an applied potential.
Yep.
How did you apply that to charge?
Yeah, I just put a charge here on this plate, and on this side, it's a constant charge. So the cell has to be... Yeah. Okay. So you have seen also this animation before. If you just look at the average, yeah, it looks all nice and clean. But if you look at the time-dependent potential, then you see it's fluctuating quite a lot. You can also immediately from this picture, yeah, take a guess that if you had a boundary condition, for example, that would pin the potential here, so it would be exactly constant at all times, yeah, this would not be able to replicate this behavior that you see here.
Sorry, can I ask you something?
Sure.
Why it oscillates so much at distance 40? So why? I mean, it's as if there is something that changes that draw that
This
slope.
is just the thermal motion of the water, nothing else. It's a complete, I try to keep this as simple as possible. It's only a plain length
I
molecular
understand,
dynamic
but I
simulation.
see that there is, so what is that there? At 40 angstrom is in the middle.
Yeah, it's in the middle. There's
The
just
middle.
water.
Okay, I understand.
There's nothing there.
And the other thing is, I mean, I hope it's okay for you if,
Sure.
because, do you think, because this is classical water, there is no screening of water.
There is no electronic screening of water.
Yes, there is no electronic screening of water at the interface, which would, screen indeed a lot of the charge over which is on the electrode. So, do you think that having that screening would mitigate a little bit that slope?
Actually, that's probably a rather technical discussion. Maybe we can get into that later. Water.
Yeah, because it's related to that a little bit. Because if that was flat,
But the
I
orientation
wonder
of
how
water.
it would oscillate.
No, this is the thermal motion of the water. This has, even if I didn't apply a field there, you could also have a zero field. No problem. Just take zero charge. You will still see exactly the same behavior.
Okay.
Just ask a very quick question. What's the time scale? How long does that run? How long does each of those wiggles?
So right now, there is several dynamics going on. Right now, we have a time step of 1 femtosecond, and 1 femtosecond is one. We have a frame rate of 24. So 1/24, 24 femtoseconds per second.
Okay. But you see, I mean, maybe it's because it's too little, but it looks strange because it's really layered structure. I mean, you see peaks these days on the one side. This is surprising because I mean, it should be more.
No,
I mean,
this is the time scale. This is just the time scale.
Yeah,
because
that's what I said. It may be too short. But if you do an average, it must be flat.
No.
There is no macroscopic average. This is how it comes out.
Yes.
Yeah. So this is the macroscopic.
But when we now our 40 picoseconds run.
Exactly. When you run 40 picoseconds, then it starts to turn flat. Not over 40 picoseconds. The dashed line is the one you asked for.
This is the average. Okay, this is the average. Okay, this is the average. Okay. The dashed line is the average. Okay, thanks. Then I understand. Okay, everything is fine.
Go on.
But because it's very interesting that you are interrupted.
Okay, I'm happier. So
this is on a time scale that is smaller than the diffusion of motion.
Yes. Exactly. You see this dynamics because it's slower than the diffusional motion. We're on a time scale much slower than diffusion.
Smaller, shorter.
Shorter. Yeah. There was another one.
I'm just going to ask, so if you're looking at structure, there's a peak just to the right of the dashed line that's very persistent. So the peak structure goes up and down. But the peaks themselves are actually quite persistent. So there is actually a bit of structure in there. And is that...
Yes, on short time scales.
Is that an artifact of how you're going from...
No, it's almost
short
gone.
time
No, it's almost gone.
It's just too short.
So that's really molecular presence.
Yes.
So it's a time scale where no diffusion takes place, or? So it still takes for the water some time to diffuse a bit. And if you would look much longer, so then of course these peaks would move around.
There's actually molecules in this simulation.
Yeah, so it's really that's a lifetime, let's say, of a molecule at a certain space.
So, okay, maybe you should move on. Otherwise, you won't get very far.
Well, we're learning something, finally.
Sure. Okay, so the point I wanted to make is the potential here is really something highly dynamic. On the time scales that electrochemical reactions take place, depending on the type of reaction, it may take from 10 to maybe 500 femtoseconds for a reaction to proceed. On this time scale, you see this dynamics. And we should be able to reproduce it. So that's our challenge. Reproduce not just the mean in the small cell, but also the dynamics, the physical dynamics that is actually there. This is commonly attempted via electrostatic boundary conditions. The two most commonly used are these ones. So on the one hand, people like to use the boundary condition of constant macroscopic electric field. Or if you will, it's the boundary condition of constant voltage. Meaning the voltage between the left side and the right side is held exactly constant at all times. You can do that by varying the charges that you have on the surfaces And this way you can hold it exactly constant. The other boundary condition would be you use a constant charge on both of these electrodes, yeah? On the working electrode and on our surrogate model. In that case, yeah, sure, the charges don't change, but the potential drop can change. Either of these boundary conditions is used either explicitly or implicitly in almost all the available techniques. Yeah? Often implicitly, but sometimes even explicitly. The nice part about this is both of these boundary conditions, that's why one is using them, both of these conditions are energy conserving, they're Hamiltonian. And that means the electrostatic potential is uniquely determined by the atomic positions. That makes it very convenient. So which one should you use? Does that actually matter? I mean, if I'm asking the question, you can already guess that it matters. But to show you that it actually matters, we have the following setup. We use a DFT-sized simulation cell. In this DFT-sized cell, we place two reference electrodes. One we place here, close to the electrode surface, and the other one we place here into the interior of the water. So let's see what these reference electrodes measure if you run the simulation. At constant charge, for the one that is placed here close to the electrode surface, yeah, we see essentially just a delta distribution. Yeah? Sure, at constant charge, there is no field, there is no change in the field. Deeper into the electrolyte, now we have the thermal motion of all the dipolar dipoles. Yeah? That gives us a distribution here. It's the thermal motion of the liquid. If you go to constant constant charge, wanted to say, cannot account for surface charge dynamics, but it does describe this part in the interior pretty well. But you cannot account for the dynamics of the surface charge here if you have any kinds of reactions. If you go to constant field, that is different. Now the voltage between here and here is exactly constant. So the charge now depends on the state of the electrolyte, and you get a distribution here for the field that we have close to the electrode. But if you go deeper into the electrolyte, yeah, we are pinning the potential here exactly. It can no longer move. So we're putting an artificial constraint on the dynamics of the electrolyte over here. We cannot avoid that. So in the end, if we have finite size far from the thermodynamic limit, both boundary conditions are insufficient. We need something else. Why is that? I think, yeah, sure.
Can you just go back? For an idiot like me, what is insufficient? You say they're insufficient. What are you looking at? The answer that's
okay, why am I saying this is insufficient? On the one hand, you want to allow the surface to have a charge dynamics. If you don't, then you have no electrochemistry. Yeah? If the charge on the surface is exactly constant, no electrochemistry.
You need charge fluctuation.
Yeah, but if you restrict the dynamics of the electrolyte over here, that is also not a good idea. Because now we have the wrong physics here inside the electrolyte.
Dynamics are measured by the variation of potential.
By the variation of the potential. Yeah.
So may I ask another question on what you were showing before, these fluctuations up and down? Why is it relevant if the timescale is so short? That it's much shorter than the diffusional timescale, shorter than the timescales of ions approaching and reacting and so on.
Because it depends on the reaction. Reactions have different timescales.
But you will show us.
I will show one, where it makes a real difference. Okay, I like to rationalize it in this way. We want to have the surface charge dynamics, but this is one time scale. And this is a very fast time scale because this is governed by electromobility. Yeah? This is how you exchange charge between the inside of the unit cell and the outside. The double layer relaxation, on the other hand, is much, much slower. This is on a time scale of nanoseconds. So this is governed by ion mobility. We really have two very distinct timescales in the system. If you go for constant field, that effectively means we have a timescale of exactly 0, which apparently is a good approximation for the exchange of charge here across the boundary, but it's not a good approximation for the ion dynamics. At constant charge, we have a timescale of essentially infinite, which is a good approximation for the ion dynamics, but not here. Yeah? So we have a bit of a conflict here. And I think it's a nice motivation to say we really need to be able to choose a finite tau. But what does it mean? When you choose a finite time scale, this means that the potential and the charge is now a thermodynamic degree of freedom. Yeah? So the potential is no longer uniquely determined just by the atomic positions. And the ensemble is no longer energy conserving. It's a situation that we know. It's a nice analogy to temperature control, where we have exactly the same thing, essentially. We have some inner energy in our system, and we allow the system to exchange heat, kinetic energy, with an external heat bath. The same kind of, this is by now standard in any code. The same kind of approach we should have also here for the charge dynamics. There is a realization for that. The group of Mino Itanie has tried that quite some time ago. In the particular realization, they tried to essentially copy a thermostat scheme exactly as is. So that makes it relatively hard to implement. But let's have a look a bit at how that works. The most easy way is, for temperature control, you set a target temperature, you measure what is the instantaneous temperature, and now you adapt the temperature in your system with a time constant. In this case, we call it tau k. You can already infer, actually, from that equation that there must be a problem in that. Because if you are very successful, you will manage that eventually the instantaneous temperature is equal to the target temperature. Sounds like a good thing? But what is the only way how that can be? It means T is almost, always, exactly identical to T0. There's only a single configuration that satisfies this condition, which is your system is frozen to a solid block and is flying with constant kinetic energy through your system. It's called the flying ice cube effect. Yeah? So this kind of expression really reduces your entropy to almost zero. Problem is, there's a missing term, as we now understand. So this is called CSVR thermostat, or BDP thermostat. One of the authors is sitting here in the audience, Davide Donadio. But it stands to reason we can take the same kind of approach and use it for potential control. You will recognize this expression as Ohm's law. And exactly as we need some extra term here, we also need to have some extra fluctuation term here.
Can you go back? Sorry, can you go back? Something that we sort of bottom here, in that.
Sorry, can you speak up a bit?
Yes, something that sort of bothers me with these here when we teach StatMech. You know, you have two variables. You have energy and temperature. And if you have fluctuations, you know, if you have an open system in terms of energy, you move from constant energy to constant temperature. But it's not written like how you have it. What we mean by constant temperature is the distribution of energy goes like E to the minus energy over KT.
Yes.
And that temperature is constant. It's a constant system. But there's fluctuations in energy given by the ultimate distribution.
Yep.
So I would say it's the same thing here. You want constant potential. When you go from a closed system of constant charge to an open system of constant potential, the potential is rigorously constant. But you allow fluctuations in n given by e to the mu n over
exactly.
E. Okay.
Thank you. That's exactly the point. That's the whole purpose of this.
Okay, it just sounds like you're talking about fluctuations in temperature and fluctuations in potential. And that is just not right from StatMech. Those are constant values defining fluctuations.
No, because the temperature that should be...
Energy, the other one being n.
You know, that also gets to be a bit of a deeper technical discussion. Because to realize such a scheme, you need two conjugate variables. The conjugate variables here would be temperature and entropy.
I think there is a problem in the definition of what is temperature and instantaneous temperature here. So what you have there, you say you don't want it to be constant, is the kinetic energy, basically, or if you want the counterpart with equipartition. But that is not the thermodynamic temperature. The thermodynamic temperature is the average of that. So that is what is generating this discussion, right?
This T is essentially just the kinetic energy, because that is what we can easily measure in the simulation. But I think there we have the problem of the discussion. Yeah, you would
we
not
have
like
very
that.
well-defined thermostats like Anderson, for example, where you just impose the Boltzmann distribution. It's a constant temperature.
Yep. You do the same thing exactly here. Yeah? By this fluctuation term, this satisfies fluctuation dissipation. If you change the kinetic energy in the system like this, you impose the Boltzmann distribution on all the degrees of freedom.
But it just sounds like you're not hearing my fundamental issue, which is you're talking about fluctuations in temperature and fluctuations in potential. But I'm saying those are constants. And the fluctuations are in E for temperature and N for potential. Those are the conjugate variables that fluctuate according to. Okay.
Exactly.
Okay.
Okay. Then let's move on. To really illustrate this a bit, yeah, we have the same cell that I showed before. Yeah, we can run this either as a constant energy calculation, as an NVE calculation. Yeah, this is this part. Or if we try now to adapt the charge on the plates, yeah, in the naive way without taking this fluctuation term into account, then you start losing energy here. You see that you can cool the system down. Essentially, you can attach an external load, yeah, like a light bulb. You put 2 electrodes in your water, the water turns to ice, and the light bulb extracts useful energy from water. That's, of course, not something that works. So why is that? Let's look a bit at the Hamiltonian of the system. As a test system, we can choose 2 capacitor plates. We put some water between the plates. Then the Hamiltonian is the kinetic energy plus the potential energy. And now here explicitly, yeah, this is the charge on the plates. So this is a displacement field. And NP is some effective polarization charge that relates to the water molecule. So this is then the polarization field. Now what can happen is that the water molecule is kicked over. And this way you have some transfer of kinetic energy from the K into the polarization. So far, you haven't lost anything. But now if you naively try to adapt the potential, yeah, because now water molecule has turned over, potential difference goes up, then the potentiostat will come and will induce a charge transfer to reduce the potential again to what it should be. If you do that, then you have essentially drained some energy from the displacement field. This energy is now lost to you. And that way, you start cooling the system down. In order to prevent that you don't have this artificial energy drain, yeah, you need to balance this with the corresponding fluctuations. So you really need to do is you derive the equation of motion for the NE, yeah, for the charge you have on the plate, from the fluctuation dissipation theorem. And that is how you should, from statistical mechanics, introduce potential control. So if you do that, one way of doing it is you can introduce a stochastic differential equation. The first part then is the potential control part. This is dissipative. You have a fluctuation part that pays back the energy that you lose by potential control. There is a specific type of calculus called initio calculus that you can use to integrate such a stochastic differential equation of motion, and to end up with an expression like this. Yeah? If you know the electrode charge at one time step, you can immediately compute it at the next time step. Yeah.
Yeah, so I think I finally understand it now. Is it basically not working because you've somehow implemented Maxwell's demon into the thermostat?
Yes.
Yeah.
Solve global warming. Take all the heat in the ocean.
And if you did the same with a thermostat, it would also cool down.
Yes, exactly. So in both cases, out of these schemes, you have to kick out Maxwell's demon. Otherwise, yeah, you will have simulation artifacts. And this is what this is about. Yeah? You want to easily control your potential, but you need to balance out Maxwell's demon. Now, this expression is quite nice because it's only a first-order approximation, actually, to be honest. But it's nice because you can see this is still Ohm's law, and this is Johnson-Nyquist noise.
who gives you R? Where you get R?
This comes out of the time scale. The time scale tau is
So it's
1
the
over...
resistance, that one.
Yeah, it's an effective circuit expression. So the R comes out of the... as I said, it's equivalent to Ohm's law if you just exchange charge between your unit cell and the part outside. And then the R is giving you the time scale.
That. It's not, so it's not like the mass. The mass, you know, you put the mass and in the Nose thermostat or all the...
This is not a Nose thermostat.
No, it's a
yeah?
This is like gamma in the range vent.
Yeah, exactly. It's like the gamma.
Oh, it's okay, it's a gamma. Okay, all right, okay, I understand. So it's a tune. You have to tune that actually.
I'll come to that. I'll come to that. The n is just a random Gaussian number.
What's that?
Unit variance.
Is variance in a Gaussian way about 0? No.
Yes, about 0. Center is 0, and it's if you integrate over the distribution, it's 1. Yes. You pick a random number from this distribution.
The decay rate of the Gaussian.
So is R the timescale close to the femtosecond level or the picosecond?
You can choose. I'll come to that also. Okay, now we have an expression that only takes the total dipole moment, and anything else you can get easily from DFT. Yeah? So that allows you to include the potential starting process into essentially any MD code. We have it in LAMMPS and VASP at the moment. So to really make this point again about the temperature control. I know we had a lot of discussions about that, but the point of this potentiostat is, this is not the macroscopic potentiostat that you might have sitting on your desk. This is about embedding your system in its external environment. Any scheme, any viable scheme that can do potential control is also invariably, you can't get around that. It is also a thermostat. The reason is, if your temperature, if your instantaneous temperature, you would like to call it kinetic energy, if your kinetic energy is larger than the average it should be, then the dissipative term dominates. On the other hand, if it's smaller, then the fluctuation term dominates. And there is an equilibrium, of course, that leads to the system on its own equilibrating just because it's embedded into a fluctuating electric field. If you get the statistical mechanics right, then this fluctuating electric field will do your thermalization for you. It's a bit like cosmic background microwave radiation. If you have matter anywhere in space, it'll have a temperature that is in equilibrium with the cosmic microwave background. But it's not because you have any kicks between the individual atoms, just because it's interacting with the background field. You can see that this works. I think this is an important validation. You can see that this works if you run a simulation, and now this is a DFT simulation, without any kind of thermostat. It's just NVE. The only thing you have is potential control. Then you get the red line. You see that you can keep the temperature. On the other hand, if you leave out the fluctuation term, you quickly cool down your system. The typical DFT sizes, like 64 water molecules, you see that within 20 picoseconds, you can get from boiling water to frozen water. You really shouldn't leave that out. You can actually indeed use it as a thermostat. We ran it for some extended time in a classical simulation. You see that whatever you set here for the T, you can change the temperature of the system just by interaction with the field. So let's get back to our question. We had, first of all, the different boundary conditions. We now look at the reference electrode that is close to the surface. And you see that with this thermopotentiostat, we reproduce the constant electric field distribution. When we go towards deeper into the electrolyte, we now reproduce also the constant charge. These are the right distributions. We already had a question about the time scale. As long as the time scale is finite, you will always get these distributions. It's implemented now in a way that I think is quite nice. It's a Python code. We have some As of last year, even in the official version of WASP, there's a Python interface, so you can run this outside. And essentially, you could also, it's transferable, yeah? You don't have to use WASP, you can use something else as well. Okay, but the question about the timescales, I think, was very real. Does it matter? So here's a specific example. It's taken from an old paper from Gersha, who looked at germanium electrochemistry. We did some up initio simulations for that. So we have an interface between hydrogenated germanium surfaces. Above it, we have water. This is copied from the Gersha paper. His finding was, or his suggestion was, that you could strip the hydrogen off. If you charge the surface positively, you would strip the hydrogen off, and it would go as H+ into solution. Makes perfect sense. You can take a look at the up initio simulation. Let's put some anodic potential here. And if you look at that, you find one of the hydrogens is taken off. You end up with a dangling bond. Then there is a second step. And the second step to the dangling bond, this is now approached by a water molecule. And this water molecule will adsorb dissociatively. So it's exactly the steps as Gersha outlined it in 1966. We left out this part. You see now one of the hydrogens goes off into the water again as H+, and you have an OH hydroxyl group on the surface. You can do some computational spectroscopy for that. You can do measurements for that. You'll find that you get an excellent match. So we have reason to believe that this process is the actually real one. But interestingly, you find qualitatively different reaction mechanisms depending on the timescale that you use in your potential control mechanism. So if you have a very high surface conductivity, meaning a very small timescale, you find this hydrogen stripping mechanism. On the other hand, if you have a low surface conductivity on the order of 100 femtoseconds, then you find a qualitatively different reaction mechanism. What happens is that you don't strip the hydrogen, instead you break the germanium-germanium backbonds. It's very different. So apparently the surface conductivity determines really reaction mechanisms. Let's have a look at the Pourbaix diagram.
Sorry, can I just interrupt? Germanium is a semiconductor, right?
Yes.
How do you determine the Fermi level or the electron potential of semiconductor in your cell?
Same as always. We take the difference between the average potential in the vacuum on the backside and on the water side.
So it's P-type or N-type semiconductor?
This is not doped. In the experiment, it's doped, yeah? You are right.
I mean, it's determined by the, if that's P-type, you have 4. Then that's determined by the limit span.
In the simulation, we don't have any doping here.
And no explicit doping, right?
No
you
explicit.
still have the change of, if you have potential control, still the change of electron numbers. So you're effectively doping in partial carriers in the typical DFT fast equilibrium between the electrons and.
There is also a little artifact here. Germanium in DFT typically doesn't even have a gap.
Yeah, that is right. But it's a germanium slab, and the germanium slab has a gap.
Perhaps, yes. Yeah.
The bulk doesn't have.
Yeah.
So the accuracy is a different question.
Yeah, sure.
We actually fought quite a bit with that.
So the time scale here is the potentiostat.
Yes.
Time scale.
Yeah.
That's a bit disturbing.
Yeah. 5 minutes. Yeah. It seems like I won't be getting to the end. So.
How many picoseconds?
Okay. So let's have a look at the Pourbaix diagram, which I think is nice, to see that actually this broken back bond is what should be stable at experimental conditions. Only if you get to much higher potentials, you can do this oxidation where you keep the back bonds instead intact and strip to hydrogen. So we find that at low surface conductivity, we actually favor this thermodynamically favored state. But at high surface conductivity, we really get a different we get a different mechanism. Yeah? Kinetically, there's a mechanism favored that does not lead to the thermodynamically stable surface. So what's the origin of this conductivity dependence? My suggestion is we just have a small unit cell. Yeah? So if we have this charge transfer and the electron has to stay on the surface, then you build up a large dipole, and this large dipole counteracts the reaction. When you counteract this reaction, yeah, it won't happen. So the question is now whether this electron can exit the unit cell fast enough for the reaction to occur. So the reaction becomes favorable if this time scale is faster than the reaction itself, actually. When you look at that, this proton transfer reaction takes about 10 femtoseconds to proceed, whereas the back bond breaking takes about 500 femtoseconds. So if you have a very small time scale, we can favor this reaction, whereas if we have a larger time scale, then this one becomes suppressed and only this one remains visible. So there's a need to capture the static mean potential, the potential distribution, and also its time dynamics. I guess I have only 5 minutes left, so I'll just jump this. Just to give a little bit of an introduction, we had another question that we liked to look at. It's a very old question. Magnesium dissolution has been known for 150 years, that it's accompanied by an anomalous hydrogen evolution. What do I mean by anomalous? It happens on the anode side, where it shouldn't happen. Yeah? Hydrogen evolution you should find on the cathode. But here you find some on the anode. And what is even more strange, not only it happens on the anode, you get more magnesium than should be coulombically possible. Yeah? Normally you should need 2 electrons, and for 2 electrons you get 1 Mg2+. But in this case, you need less than 2 electrons to get a magnesium ion. So it was taken as evidence that the magnesium ion might exist in a rare Mg1+ form. But of course, chemically that doesn't make much sense. But it was so unclear that even Marcel Courbet in his famous atlas put the Mg1+ with a question mark inside the atlas. When you perform thermopotentiostat calculations for the surface, then it can only give you a quick idea. I guess we don't go through this. Let me just give you the final model. That is better. We find there are 2 different pathways. One pathway is the conventional pathway. You have Mg, you get dissociative adsorption on the surface, then you get Mg2+ and OH- and 2 electrons. One possible way is that now this dissociates, the Mg2+ goes into solution, and you have OH- sitting on the surface. But there's a different pathway. The second pathway, there the Mg2+ OH- goes off into solution as a complex. We can find both pathways actually in the ab initio simulations. Can directly observe both of them. I think we don't need to go through all the reaction equations. What's nice about it is these equations are all observed in ab initio. If you sum them up and you balance them with the cathodic half reaction, you get exactly the well-known balance equation from magnesium dissolution. Just now you know that inside this equation there is actually a second pathway that was unknown, and that you can nicely show with ab initio simulations. So with that, I'm at the end of the talk, maybe just in time. For predictive simulations of electrochemical processes, we think you have to replicate actually the potential dynamics of the unbounded physical system within this ab initio size supercell. So you need the average, the mean, but also the statistical distribution and the time-dependent dynamics. Just again, the potentiostat is not this macroscopic device. It's about the embedding into this surrounding environment. I showed you some applications for germanium, very, very briefly, magnesium dissolution. And with that, thank you for this.